Okay, welcome to 10,000 Labs. Today we're diving deep into something that's becoming really essential for anyone building with AI. We're talking about context engineering.
Yeah, absolute crucial stuff.
When we think about large language models, LLMs, it's sometimes helpful to picture them like a computer CPU, right?
Right, the processing core.
And their context window, well, that's kind of like the RAM, the working memory.
Exactly. And just like RAM.
It's limited. That's the key thing. It has a finite capacity.
Precisely.
So our mission today is really to unpack how engineers are getting, well, meticulous about this, how they're carefully filling that context window with just the right information at every single step.
And it's almost an art form at this point.
It really is. And it makes these AI agents actually work. It's a surprisingly broad field, too, and it's changing fast.
Incredibly fast.
So let's focus on AI agents for a minute. Why is this context engineering so vital for them specifically? What makes agents different here?
That's a great question because agents are, well, they're different beasts. They're designed for much longer, more complex, multi-step tasks, not just a single question and answer.
Right, much more involved.
And a huge part of how they work is tool calling. They're constantly reaching out to external systems, search engines, databases, maybe even other AI models.
Okay, getting external info.
And then they get feedback from those tools, results, data, whatever it is. And this back and forth, calling tools, getting results back, thinking about the next step.
It all adds up, I bet.
It adds up fast. You get this huge increase in token usage, the feedback, the agent's own internal thoughts, maybe the history of the conversation. It just accumulates over potentially hundreds of turns.
And I can see immediately how that becomes a problem. All that context building up. It must hit costs, speed, everything.
Oh, absolutely. That accumulated context, it very quickly bumps up against and then exceeds the LLM's context window limit.
And then what happens?
Well, you get a cascade of issues. First, costs skyrocket. More
Yeah.
tokens, more money. Simple as that. Second, latency goes up. The model has more stuff to process, so responses get slower.
Makes sense.
But the most critical thing, it can severely degrade agent performance. The agent just doesn't work as well. Or sometimes it fails completely.
Okay, so performance degradation. Are there specific ways it fails? Like common failure modes?
Yeah, Drew Brunig actually outlined some really specific context failures that crop up when you don't manage this well.
Oh, interesting. What are they? Is there one that's particularly nasty?
They're all pretty problematic, honestly. He listed 4 main types. First, there's context poisoning.
Poisoning. Sounds bad.
It is. It's when a hallucination, the model generates something incorrect, gets into the context.
Oh.
And that bad piece of info contaminates everything that follows. It can send the agent completely off the rails, making decisions based on something false. I've seen agents get really bizarre because of this.
Wow. Okay, what else?
Then there's context distraction. This is simply having too much information in the window. Even if it's all technically relevant, it just overwhelms the LLM.
So it loses focus.
Exactly. It loses sight of the main goal. Third is context confusion. This is when extra, maybe slightly off topic, information creeps in and kind of sways the LLM's response.
Pushes it in the wrong direction a bit.
Right. Leads it down a less optimal path. And finally, context clash. This is where different parts of the context actually contradict each other.
Ooh, that sounds tricky.
It's really insidious. The LLM gets conflicting signals, making it impossible to give a coherent answer. It might just freeze up or give contradictory outputs.
So it's really not just about how much fits, is it? It's the quality and the relevance of what's actually in that window.
Precisely. The quality is paramount.
And is this widely accepted? Is there a consensus on how critical this is?
Oh, absolutely. There's a very strong consensus. Cognition, for example, they flat out said, context engineering is effectively the #1 job of engineers building AI agents.
Wow. Number one.
Yeah. And Anthropic noted that these agents often have conversations spanning hundreds of turns, which absolutely demands careful context management strategies.
Hundreds of turns. Yeah, you can see how the window fills up.
So, if you've ever worked with an agentic system and it failed, maybe it did something weird or just stopped.
Yeah, it happens all the time.
Often, it's not that the underlying model itself is just, dumb or broken. More often than not, the real issue is that the underlying model was not past the appropriate context.
Okay. Garbage in, garbage out, almost.
Sort of, but more like confusing stuff in, confusing stuff out. LLMs aren't mind readers, right? They only know what you tell them.
Right.
And context engineering is the craft of telling them exactly what they need to know when they need to know it.
Okay, so what kinds of information are we actually managing here? What falls under this context umbrella?
Good question. The sources generally break it down into three main categories you need to juggle.
All right, what are they?
First, you've got instructions. This is stuff like your initial system prompts, maybe some few-shot examples to show the model what kind of output you want, memories, and crucially, descriptions of the tools the agent can use.
Okay, instructions and guidance. Makes sense.
Second is knowledge. This is broader facts, general information, maybe long-term memories the agent has stored from past interactions.
Got it. Factual stuff.
And third, there are the tools themselves, or rather the feedback from tool calls. The results, the observations, the data that comes back when an agent uses a tool. And as we said, this part accumulates really fast.
Right, the tool feedback loop. So instructions, knowledge, and tool feedback. That covers a lot. Now, you mentioned prompts under instructions. How does this whole context engineering thing relate to what we used to call prompt engineering?
Yeah.
Is it just a fancier name?
No, it's definitely more than that. It's a fundamental shift, actually.
Okay, how so?
Prompt engineering traditionally was more about crafting that perfect, clever, static phrase to get a good response from a model in a single interaction.
Right, tweaking the initial input.
Yeah. No, prompt engineering is really considered just a subset of context engineering.
Yeah, okay, part of a bigger picture.
Exactly. Context engineering is about building dynamic systems. Systems that automatically figure out and provide the complete structured context the AI needs at the right moment during a potentially long and complex task.
So it's not just the starting line. It's managing the whole conversation.
Precisely. It's about managing an evolving flow of information, getting the right stuff in the right format at the right time as the agent acts, learns, and makes progress. You're building an intelligence system around the LLM to feed it, not just writing one perfect query.
That makes a lot more sense. It's about the whole system, the whole process.
Exactly. And with those challenges and types of context laid out, engineers have basically developed four main strategies or maybe buckets of techniques to tackle these context problems.
Okay, this is where it gets really interesting, right? The practical solutions. What are these four strategies? Let's break them down. Maybe start with the first one.
Sounds good. The first strategy is essentially right context.
Right context.
Yeah.
So like saving information.
Exactly. Saving it outside the immediate context window to help the agent perform its task later. Think of it like how we take notes or keep a diary.
Okay, like external memory. How does that work in practice?
There are two main ways people do this. First, there are scratch pads.
Scratch pads, like temporary notes.
Pretty much. They're temporary notes, but specifically for a single session or a single task run. The idea is to save intermediate stuff the agent generates, maybe a multi-step plan it came up with, or some partial results.
So if the main context gets too full and needs trimming.
Right. If the context gets truncated, that crucial plan or intermediate thought isn't lost. It's saved in the scratch pad and can be pulled back in later within that same task.
Gotcha. Any examples?
Yeah, Anthropic's multi-agent researcher work mentioned saving its plan explicitly to memory, their term for a scratch pad in this case, because their context window could hit 200,000 tokens. If it got truncated, losing the plan would derail the whole process.
Wow, okay. And how do you implement that? Just a text file?
It could be a file, yeah, or often it's stored in a runtime state object associated with that specific agent session.
Okay, so scratch pads are for within a task. What's the other right context method?
That would be memories, proper long-term memories.
Okay, so these persist between tasks.
Exactly. Information saved across many sessions. This is more like building up a persistent knowledge base for the agent over time.
And how are those created?
Well, some research, like reflection, explored agents generating their own memories based on reflections on past actions. Generative agents synthesized memories periodically. But now you see this in products, too.
Like ChatGPT's memory feature.
Precisely. ChatGPT, Cursor, Windsurf, they all have features that auto-generate long-term memories based on your interactions. The agent remembers your preferences, past conversations, key facts it learned. It builds up persistence.
That distinction is super clear. Scratch pads for the current job, memories for the long haul. Okay, so you've written the context down. Strategy 2 must be about getting it back in, right?
Spot on. Strategy 2 is select context.
Selecting. So pulling the relevant stuff back into the context window when needed.
Exactly. It's about intelligent retrieval.
Yeah.
You have this external store scratch pad or memory, and you need to pull only the most relevant pieces into the LLM's active working memory for the current step. Because like we said, you can't just dump everything back in.
Right. That would defeat the purpose and cause distraction or confusion.
Yeah.
So how do you select effectively? Let's start with selecting from memories.
With memories, selection is key. Agents might need different types of memory, maybe episodic memories, like specific examples of how to do something, or procedural memories, like step-by-step instructions, or semantic memories, just raw facts.
Okay, different kinds for different needs.
Yeah, but the big challenge is ensuring relevance without adding noise, or worse, something weird. Simon Willison mentioned an interesting case
Yeah.
where ChatGPT unexpectedly pulled his location from its long-term memory and stuck it into an image generation request he made. It wasn't relevant at all to the image, but the system retrieved it anyway. And it made users feel, as he put it, like the context no longer belongs to them. It felt intrusive and irrelevant.
Yeah, that highlights the need for precision. How do you manage that with lots of memories?
For large collections, people often use techniques like embedding-based similarity search or knowledge graphs to try and pinpoint only the most pertinent information for the current query or task step.
Okay, embeddings and graphs for memory selection. What about selecting tools? You mentioned agents can get overloaded.
Hugely overloaded. This is a really common practical problem. Research shows agent performance starts degrading if you give it more than about 30 tools to choose from.
30. That's not actually that many if you think about complex workflows.
Right, and performance apparently falls off a cliff, like complete failure, around 100 tools. The model just gets lost.
So how do you select tools intelligently?
A really powerful technique is using arg retrieval augmented generation, but applying it to the tool descriptions.
ARG on the descriptions. How does that work?
You embed the descriptions of all the available tools. Then, when the agent needs to act, you use semantic search to find the descriptions of the tools that are most relevant to the current task or subgoal.
Ah, so you only show the agent a small, relevant subset of tools to choose from.
Exactly. And this isn't just theoretical. Studies have shown this can improve tool selection accuracy by as much as threefold.
3 times better, just by selecting the tools better.
Wow. It's a massive improvement, shows how critical selection is. And this idea extends to selecting knowledge more broadly using ARI.
Right, general knowledge retrieval.
Yeah, and code agents are probably the best large-scale production examples of this challenge. Getting the right code context is incredibly hard.
I can imagine code bases are huge and complex.
Totally. Varun from Windsurf made a great point. Indexing code at context retrieval? Just because you've indexed it doesn't mean you can find the relevant bits easily.
So what do?
They use a whole battery of techniques. Things like parsing the abstract syntax tree, understanding the code's structure, not just keywords, semantic chunking, embedding search, of course, but also traditional things like grep and file search, knowledge graphs, and even using another LLM just to re-rank the retrieved snippets by relevance before showing them to the main agent.
Whoa, that's a multi-layered approach. It sounds like selecting context is a major engineering effort in itself.
It absolutely is. Getting the right stuff in is non-trivial.
Okay, so we've written context out, we've selected context back in. What's the third strategy? You mentioned compressing context.
Yes, compressing. This is all about reducing the number of tokens already in the context window while trying to retain the essential information needed for the task.
Okay, trimming the fat, basically.
Exactly. Cutting out the fluff, keeping the signal.
How do you do that?
One common way is context summarization. This is super useful for managing those really long agent interactions or dealing with tool calls that return huge amounts of text.
Like summarizing the conversation history.
Yeah, or summarizing the output of a verbose tool. Claude Code, for instance, has an auto-compact feature. When the context window gets about 95% full, it automatically summarizes the entire user-agent interaction history up to that point.
Ah, clever. So you keep the gist without hitting the limit.
Right. And you can apply summarization strategically. Maybe after a big search result comes back, you summarize it before adding it to the main context. Or in multi-agent systems, you might summarize information before handing it off from one agent to another. Cognition apparently uses a fine-tuned model just for the summarization task, ensuring key events are captured efficiently.
So using an LLM to shrink the context, what's the other compression technique?
The other main one is context trimming or pruning.
Trimming.
Trimming.
How's that different from summarizing?
Summarization usually involves an LLM rewriting and condensing the information. Trimming or pruning is often simpler, using filters or heuristics to just remove parts of the context, like hard-coded rules. For example, simply removing the oldest messages in a chat history once it reaches a certain length. Keep the end most recent turns.
Okay, a simple rule-based approach.
It can be. Or it can be more sophisticated. There are learned approaches too, like a model called Provence, designed for question answering, which learns to identify and prune sentences from the context that are irrelevant to the current question.
Got it. So summarization, distills, trimming, filters, or removes, both aimed at reducing tokens. Makes sense. Okay, that leaves the fourth strategy, isolating context. This sounds like splitting things up.
Exactly. Splitting information up strategically to help the agent perform its task, often by preventing different types of context from interfering with each other, or by allowing for parallel processing.
How does that work in practice? What are the main ways to isolate context?
Probably the most popular approach right now is using multi-agent architectures.
Ah, like having a team of specialized agents.
Precisely. Think of OpenAI's Swarm library. The whole idea is separation of concerns. You have multiple agents, each potentially with its own context window, its own specific tools, its own tailored instructions for its subtask.
So each agent only has to deal with the smaller, more focused context.
Exactly. Anthropic's research made a strong case that a team of agents, each with isolated context for their specialty, often outperformed one big monolithic agent trying to juggle everything.
Why is that?
Because each subagent's limited context window can be dedicated entirely to its narrow piece of the puzzle. They can operate in parallel, and collectively, the system can process way more information and complexity than a single agent ever could. It leads to richer, more robust results for complex problems.
Makes sense. What are the downsides?
Well, it can significantly increase token usage overall, potentially up to 15 times more tokens than a single chat, because you have multiple models running and coordinating, and that coordination itself requires careful prompt engineering.
So it's a trade-off. More power, but more cost and complexity.
Definitely. But for really complex, open-ended tasks, it's often a necessary trade-off. Another way to isolate is using context isolation with environments, often called sandboxes.
Sandboxes, like for running code safely.
Exactly. Hugging Face's deep researcher has a code agent that does this. The agent generates code, but that code runs in a secure, isolated sandbox.
Okay, and how does that isolate context?
Because only selected information from the sandbox gets passed back to the LLM, maybe just the final return value, or a specific observation the code made.
Ah, so the LLM doesn't need to see all the intermediate steps or large data structures inside the sandbox.
Precisely. It's a great way to isolate token-heavy objects, think images, audio files, large data sets from the LLM's main context window. The heavy lifting happens in the sandbox, state can persist there across turns, but the LLM only gets the crucial results it needs. It doesn't have to see every pixel of an image, just the analysis outcome.
Very clever. Any other isolation methods?
One more worth mentioning is using the agent's runtime state object itself as an isolation mechanism.
The state object.
Yeah. If you design your state object with a clear schema, like using pedantic models in Python, which lets you define structured data, you can create specific fields for different types of information.
Okay.
Then, at each step or turn, you only expose certain fields from that state object to the LLM. For instance, you might only pass the current messages list while keeping internal notes, long-term plans, or configuration settings hidden in other fields within the state.
So you control exactly what slice of the agent's internal state the LLM sees at any given moment.
Exactly. It gives you really fine-grained control, isolating parts of the context within the agent's own runtime state, ready to be selectively pulled in or updated as needed.
Wow. Okay. Writing, selecting, compressing, isolating. That's a really comprehensive toolkit.
Yeah.
So what does this mean for engineers actually doing this day to day? Are there specific tools that make implementing these strategies easier? Or is it all custom code?
That's the million-dollar question, right? How do you actually build this? Well, before you even get to implementing these strategies, there are two things you absolutely need. Foundational pieces.
Okay, what are they?
First is observability. You have to be able to see what's going on. Track token usage, trace the agent's steps, see exactly what context is being passed at each stage.
Like debugging for context.
Exactly. Tools like Langsmith tracing are invaluable here. They let you dissect complex agent runs and pinpoint where your context issues are or where your engineering efforts should focus.
Makes sense. You can't fix what you can't see. What's the second piece?
Evaluation. You need a systematic way to test if your context engineering changes actually help or accidentally hurt performance.
Like measuring the impact.
Yeah. Again, something like Langsmith evaluation provides frameworks for this. You need to be able to run experiments, compare results, and ensure your clever context strategy isn't making the agent worse at its actual job.
Observability and evaluation. Got it. The feedback loop.
It's absolutely crucial. It creates that virtuous cycle. Observe a problem, implement a context strategy, evaluate the result, repeat.
Okay, so assuming you have that feedback loop set up, then what about frameworks for actually implementing writing, selecting, compressing, isolating?
That's where tools designed for agent orchestration come in, like LangGraph.
LangGraph, how does that help?
Well, it's designed as a low-level framework specifically for building stateful, multi-step agentic applications. It gives you that fine-grained control over the agent's flow and state, which is exactly what you need for sophisticated context engineering.
Okay, so how does it support those four strategies? Let's take write context.
For writing, LangGraph has built-in support for checkpointing. This essentially saves the agent's state at various points, acting like a scratch pad for persisting information within a single task run. It also supports integrations for proper long-term memory, allowing context to be saved and reused across completely different sessions.
Okay, checkpointing for scratch pads, long-term memory integration. What about select context?
Because you define the agent's flow as a graph, you have explicit control within each node, each step. You can decide exactly what parts of the state to access, or query the long-term memory using things like embedding retrieval. There's even a specific library, the LangGraph Big tool, designed to help with that tool selection problem using RAG over tool descriptions.
Nice. And compressing context.
Again, the low-level nature helps. You can easily add custom logic inside your graph nodes to summarize or trim context. LangGraph also offers some built-in utilities for message history summarization and trimming, and you can slot in logic to, say, post-process a verbose tool call before passing the result on.
Flexible. And finally, isolating context.
Its core concept revolves around a structured state object, often defined with a schema, which naturally lets you isolate context into different fields. It also has integrations and examples for using sandboxes like E2B or Pyodide for code execution isolation. And it has extensive support for building various multi-agent architectures like supervisor patterns or swarms.
So it sounds like it provides the building blocks to implement all four strategies by giving engineers that granular control over state and flow.
That's the idea. It provides the framework to orchestrate these context management techniques effectively.
Okay, this has been fascinating. What we've really explored today shows that context engineering isn't just some niche optimization anymore. It feels like it's becoming a truly crucial craft for anyone trying to build serious, reliable AI agents.
Absolutely. It's moving from a nice-to-have to a must-have very quickly.
And these four pillars, writing, selecting, compressing, and isolating context, they seem like the fundamental strategies engineers need to master to make these powerful LLMs actually deliver on complex tasks consistently.
Couldn't agree more. And as we discussed, having the right tools like LangGraph for implementation and Langsmith for observability and evaluation creates that essential feedback loop.
Right, the loop to identify issues, try solutions, test them, and actually make progress.
Exactly. It empowers that iterative refinement process, which is so critical in AI development. And maybe a final thought to leave people with. If we step back, this whole field of context engineering really boils down to communication, doesn't it?
Communication. How so?
Well, the core challenge is effectively communicating with the LLM, giving it the right information in the right way at the right time. We established models aren't mind readers. They depend entirely on the context we provide.
Right. The quality of the input dictates the quality of the output.
So if that's the case, what does this intense focus on communicating clearly and precisely with an AI teach us about how we communicate with any complex system, or even how we communicate with each other, especially now in a world drowning in information?
That's a really interesting question. It's not just about what you say.
Right. It's about how you frame it, what context you provide, what you choose to emphasize, and maybe just as importantly, what you choose to leave out to maintain focus and clarity. Perhaps effective communication, whether with AI or humans, is increasingly about skillful context engineering.